Hello, this is Miss Moore, and today during chemistry we're going to discuss galvanic cells. Today's essential question: how is the EMF of an electrical chemical cell calculated? Let's start with a real quick review of redox reactions. So a redox reaction is a reaction in which electrons transfer from one reactant to another. So for example, if we have solid zinc in a solution containing copper ions, we can end up with zinc ions and some copper solid. All right, so let's look at the oxidation numbers and figure out the oxidizing and reducing half reactions. So zinc is just an atom, right? So it's going to have an oxidation number of 0. Copper 2 plus ion has an oxidation number of 2 plus. Zinc ion has an oxidation number of 2 plus. And copper solid is going to have an oxidation number of 0. Okay, let's now identify the oxidizing and reducing half cells of the redox reaction. So oxidizing, we'll start with that one. Remember that oxidizing is losing electrons, and zinc solid goes from a 0 to a 2 plus, meaning it's lost 2 electrons. So the zinc portion is the portion that is oxidizing, and the reducing portion, reducing is gaining electrons, and that would be going from copper 2 plus to copper solid. That is the reducing portion. I don't need that aqueous. The reducing portion of the redox reaction. And because zinc is losing electrons, he is giving the electrons to copper 2 plus. So copper 2 plus is the oxidizing agent, and copper is gaining electrons, right? And he is getting those electrons from zinc, so zinc is the reducing agent. To understand galvanic cells, it's important that you understand who's being oxidized, who's being reduced, who is the oxidizing, and who is the reducing agent. All right, onward. What is a galvanic cell? To talk about galvanic cells, we need to have a little idea of electric current. So electric current is really just the flow of electric charge. It's the movement of electric charge. When would we see something like that? Well, electrons flowing through a wire, right? So, for example, electricity, the stuff you need to turn on a light. Ions flowing through a solution, that's also a change of electric charge. So an example of flowing of electric charge through a solution would be the example we just went through, where the electrons from zinc are being transferred to copper 2, giving us copper solid. That is an example of electric current. So a galvanic, or also known as voltaic cell, is an electrochemical cell that produces electric current from spontaneous chemical reaction, like this guy here. So what we do is that the half reactions of a redox reaction are physically separated. Okay, not just on paper, but actually physically separated, the actual reaction itself, not just the equation we use to write the reaction. And this requires electron transfer to take place through a wire as opposed to through the solution. The current produced by the wire by the electron flow can then be directed through a device such as an electric motor such as a light bulb, to provide useful work. All right, so using our same reaction, redox reaction again, we've got zinc, which is being oxidized, transferring electrons to the copper, right? Copper is accepting the electrons to become copper solid. All right, so here's a schematic representation of an actual galvanic cell. So we've got two beakers here. The white boxes are supposed to be beakers, if you couldn't tell. And we've got in the beaker a solution of zinc nitrate, which really ends up being a bunch of zinc 2 pluses floating around and NO3 1 minuses floating around. And in the other beaker, we have copper 2 nitrate solutions. Again, we've got copper 2 floating around and NO3 minus floating around. In each beaker, we also have a metal electrode, which we just call it electrode. It's really just a piece of solid zinc in one and copper in the other. So let's write this out. We have zinc electrode in the zinc nitrate solution, and we have a copper electrode in the copper nitrate solution. And you will note that the zinc metal shouldn't really react with the zinc nitrate, right? I mean, zinc is zinc. And the copper electrode's not going to react with the copper nitrate solution because, you know, copper is copper. So our two half reactions are physically separated, right? All right, so then what else do we have? This gray thing up at the top, this is just a wire connecting our two electrodes. And the last piece we have here is this yellow arch, which we call a salt, turns out I don't know how to spell, bridge. Okay, this is a salt bridge. This can be a hollow tube with salt water in, some sort of salt water in there. It can be a string soaked in the same salt water or filter paper. So our salt bridge is going to contain, oh, that's a really bad color. It's going to contain potassium chloride, or KCl. So we're going to have K pluses floating around in here and Cl minuses floating around in here. Okay, well, let me get rid of the KCl. Right, so here's the basic setup of a galvanic cell. So in the beaker with the Zn electrode, we have the Zn solid going to Zn2 plus portion of the half reaction, which is the oxidizing portion. And in the copper electrode beaker, we have the Cu2 plus going to Cu solid portion, or the reduction portion of the half reaction. All right, so what's actually happening in this galvanic cell? Well, some electrons from the zinc solid are going that way, leading to a few Zn2 pluses to be added to the solution, which could make this area quite positive. So that attracts some of these Cl's in the salt bridge to neutralize some of those extra positives. So coming around as the electrons keep moving this way, and coming into the solution, reducing some of these Cu2 pluses onto the copper electrode. What should happen over time is that this copper electrode should get heavier. And in theory, the zinc electrode should get lighter. And we have this redox reaction going on, even though they're actually physically separated. And as these, I forgot to tell you this, as the copper 2 pluses are going onto the electrode, we're ending up with an excess of NO3. So the salt bridge, back to the salt bridge, to take care of that, some of these potassiums are attracted to the nitrates, the free nitrates, keeping the solution electrically neutral. Some terminology you're going to need to know is that the electrode that is being oxidized, in this case the zinc, is known as the anode. So that's the one that's being oxidized. And the cathode is the electrode that is being reduced. So anode is oxidized, cathode reduced. And this mess here is a description of a galvanic cell, how it works. We don't need to use only zinc or copper electrodes, but we'll discuss that a little bit later. So again, here's a basic galvanic or voltaic cell. All right, next up, cell potential. So a galvanic cell consists of an oxidizing agent in one compartment that pulls electrons through a wire from the reducing agent in the other compartment. So taking a look at our previous example, we had zinc solid plus copper 2 plus producing zinc 2 plus copper solid. Remember that the oxidizing agent is the thing. Okay, so let's put that example we've been working on back up. We have zinc solid plus some sort of copper ion solution produces zinc 2 plus and a copper solid. So zinc is being oxidized while copper is being reduced. So if we think about the flow of the electrons, what's happening? The galvanic cell consists of an oxidizing agent in one compartment that pulls the electrons through the wire. So the oxidizing agent is the guy receiving the electrons, right? So that means that copper 2 is pulling the electrons from the zinc to become reduced. And the electrons are being pulled from zinc, which is the reducing agent. It's the thing giving up the electrons. So this pull of the oxidizing reagent is what we call the cell potential, or abbreviated as E cell. And this cell potential, also known as electromotive force, abbreviated as EMF, of the cell can be measured using a voltmeter. Okay, we can see what the change of voltage is, what the change of current is through the electrical current, the transfer of electrons through the wire. And so EMF is a measure of voltage. And this voltage, which we're going to be talking about, is dependent on several things. The nature of the electrodes and ions, meaning like the zinc Zn2 plus and the copper Cu2 minus, or we could be using magnesium or whatever, the concentrations of the ions in the solution, and the temperature at which the cell is operated. All of those things will change the voltage in the wire between the oxidizing agent and the reducing agent. Okay, cell diagrams. A cell diagram is a notation for representing galvanic cells. It's an abbreviation. Instead of drawing out the big picture that we just saw, and you'll see it in a minute, you can write it out. So a single vertical line is used to represent a phase boundary, okay, going from solid to aqueous, aqueous to solid. That's what we mean by a phase boundary. A double vertical line is used to represent a salt bridge. So it's like the portion in between the two cells. And by convention, the anode is always written first. All right, let's try a cell diagram. So once again, we have our little picture of our electrochemical cell in the zinc half reaction. Remember, zinc was the one that's being oxidized. So this is the anode, and it's written first in our cell diagram. So we're going to have zinc solid, single line showing a phase change to Zn2 plus. So what we've got going on here is the zinc is losing 2 electrons up that way, and over here becoming Zn2 plus. Okay, and then the copper is being reduced. So this is going to be the cathode, which is written second. So double line showing the salt bridge. And what's happening here is we're going from the wire into the solution, taking one of these Cu2 pluses, right? It then gains 2 electrons, becoming copper. So we're going to have, I think I need to move this. Let's see if I can get this to work. Cu2 plus 2 Cu. All right, that's kind of a mess. Let's rewrite that. So what we have going on is zinc solid, phase change to zinc ion aqueous, going through the salt bridge, the wire, we end up with the Cu2 plus aqueous into copper solid. I hope you can read that. Normally we also put the concentration of the solution, so which I never told you. So we're just going to say it's 1 molar. So again, we're going to have Zn solid, phase change, Zn2 plus 1.0 molar, going to copper 2 plus 1.0 molar, phase change to copper solid. So this is an example of a cell diagram. You write something like this versus trying to draw out this whole thing here. Okay, so it's shorthand abbreviation for what your electrochemical cell looks like. Standard reduction potentials. The measured EMF of a cell can be calculated, as opposed to just measured, as the sum of the electrical potentials of the 2 half cells. Just like we can figure out the redox reaction by summing the 2 half cells, we can figure out the EMF, the electrical potential of the whole system, by measuring the potentials, the electrical potentials of the 2 half cells. So that when the 2 cells are connected, the oxidizing half and the reducing half, electrons flow from the electrode with a more negative charge, which is the oxidizing half, the part with greater potential energy, to the electrode with more positive charge, the reducing half, with less potential energy. So to figure out the charge or the voltage of just a half cell, we need to measure it against some sort of standard. So what we use is a standard hydrogen electrode known as SHE, standard hydrogen electrode, to obtain the electrical potential of each half cell. So the way this would work, if we were trying to figure out the electrical potential of the zinc half cell, it would be connected not to copper, but to platinum with HCl or H plus and Cl minus. And this would give us we could measure that and get the half cell potential of the zinc. We would then do this again to figure out the electrical potential of the copper. This would be platinum, and this would be HCl. Okay, so that's the basic setup. We take the standard hydrogen electrode and arbitrarily assign that potential as 0. So that's our standard, that's our baseline. And electrons travel from the anode, as you know, to the cathode, and the E cell, or the electrical potential, is defined as the final voltage minus the initial voltage. But because we defined SHE as 0, we can figure out the electrical cell of the voltage by saying it's the cathode minus the anode. When the standard hydrogen electrode is paired with a cell that is a strong oxidizer, so a strong oxidizer is something that easily loses electrons, the standard hydrogen electrode will be the cathode, and the electrical potential will be negative. When the standard hydrogen electrode is paired with a cell that is a weak oxidizer, meaning doesn't really want to give up electrons, actually more likely to gain electrons, the standard hydrogen electrode will act as the anode, the one donating electrons, and the electrical potential will be positive. All right, so now let's talk about how you would calculate, instead of measuring, how you would calculate the standard potential for electrochemical cells. First thing you're going to do is separate the reaction in the redox reaction into the oxidation and reduction half reactions. You're going to look up the standard electrode potentials for each half reaction, which I'll show you in just a moment. You're going to add the half cell reactions together to obtain the overall redox reaction. And then you're going to calculate the standard cell potential by subtracting the electron potential of the anode from the electron potential of the cathode. Remember, E cell equals E cathode minus E anode. So let's try one. We have a galvanic cell consisting of a magnesium electrode in 1 molar magnesium nitrate solution and a silver electrode in a 1 molar silver nitrate solution. And looks like something got cut off there. Silver nitrate solution. Calculate the standard EMF of this cell at 25 degrees Celsius. All right, so now what we need to do, or the first thing we need to do, is to figure out the reduction and oxidation half reactions. problem with this question is that I actually have no idea what the reduction half or the oxidation half is, but I do know what the half reactions are. I know I'm going to have magnesium going to Mg2 plus, and I know that I'm going to have silver, solid, going to Ag1 plus. You'll note that I left out the nitrate solution, and that's because the nitrate is not part of the reaction. All right, so next we need to balance out the charges, make these neutrals. So going from Mg to Mg2 plus, I need to add 2 electrons. And going from Ag to Ag1 plus, I need to add 1 electron. And being that we're going to be putting these together later, why don't we go ahead and neutralize the electrons? We know they both need to have 2, which means I need to multiply this guy here by 2, giving us 2 Ags, 2 Ag1 pluses, and 2 electrons. All right, now we need to figure out which one of these is the oxidation portion, or the anode, and which one of these is the reduction portion, or the cathode. So what we're going to look up is a data table that contains standard reduction potentials. And these are measured, each half reaction has been measured against the standard hydrogen electrode. So you do have one of these in your book, and we also have it on our PowerPoint here. So let's look for, well, here's our Mg right here, which has a standard reduction potential of negative 2.37 volts. So we'll put that in, negative 2.73 volts. And now we need to find the silver, which is right here, and that is positive 0.8 volts. So I'll put that in. So now, which one is the oxidizing agent? That will be the one, no, which one is oxidized? Sorry, let me take that back. Which one is oxidized? That is going to be the one that has the largest, the most negative potential, which in this case would be the magnesium. So this is the one that has been oxidized, or is the anode. And that means that the silver is being reduced, and thus is the cathode. Okay, so what's going to be happening now during this reaction, now that we know which one's oxidized and which one's reduced, is that magnesium is going to give an electron or two to silver, causing silver ion to make silver solid, which means that this reaction here, the reduction reaction portion, needs to be flopped. So we're going to be writing that one as 2Ag 1 plus 2 electrons gives us 2Ag solid. So that way the magnesium can donate an electron to the silver ion, making it silver solid. So now let's put our redox reaction back together. We're going to end up with magnesium solid plus silver ion. Oh, we forgot we need to cross out anything like that. gives us magnesium ion plus silver solid. Okay, now we need to figure out the EMF. So remember that our EMF is the potential at the cathode minus the potential at the anode. And for us, that means it's the potential going from silver ion to silver solid minus the potential going from magnesium ion, the magnesium solid to magnesium ion. And from here, all we need to do is plug and chug. But before we do that, if you go back and look at the standard reduction potential for magnesium to Mg2+, you will note that I transposed the 7 and the 3, and this should be 2.37 volts. Okay, so now we can plug this in. So our EMF equals, at the cathode we had 0.8 volts, minus at the anode we had negative 2.37 volts. I guess I should write volts in there, giving us an EMF of 3.17 volts. So there you go. We have now calculated the EMF for our electrical chemical cell. And last quick thing, we can use the sign of our EMF to predict the extent and direction of a redox reaction. So a positive EMF means the redox reaction will favor the formation of products at equilibrium. So it'll go forward, which you will note that ours is positive, which means it'll go from magnesium solid to silver solid. Okay, and a negative EMF means that the redox reaction will favor the reactants, and so it'll push towards the reverse reaction. Okay, I am sorry this was so long. I hope you understood it, and that's it for today. Have a good one.